Okay.
He was a minute ago.
Oh, okay.
There.
Is it
Might
working
be
now?
a couple minutes delay.
Anybody check the YouTube real quick?
They're saying yes.
Okay, good, awesome. Thank you very much.
Sorry about that.
All right, so I am very proud and humbled to be here today at Maissa Salama's dissertation defense. I'll just give you a quick introduction of just maybe going over the last 6 years that we've been working together. So this all started in the fall of 2015, and we hit the ground running. So Maissa was very interested in both doing instrumentation and science. She'd previously done the instrumentation summer school at Dunlap Institute in Toronto. So she was ready to do optics right away. So I was like, great, let's do this. First semester, we went out to Caltech, I think at least twice, to reconfigure the Robo-AO system that was at Palomar Observatory, and we were about to take it to Kitt Peak. And the idea was Maissa would do science for her dissertation with the system from Kitt Peak. So what you see here is her and her future postdoc sponsor, Becky Jensen-Clem. They basically reconfigured the adaptive optics system, redoing the laser wavefront sensor to get it ready for telescope operation. This is all during her first semester here at the IfA. So we got that done just within a total of 3 weekends. Here, all three of us happy. And you'll notice we're all wearing masks, and this is way back before it was cool to wear masks. So you'll see that a lot throughout this introduction. So that same semester in November, Caltech crew took the instrument out to Kitt Peak. Within 1 week, it was all in the telescope. The second week, the IfA crew with Maissa, you can see her down here, we got the AO system working. We were taking science. So we basically got an old system to a new telescope, taking science data within 2 weeks. It's absolutely fantastic. So during the final or the end of Maissa's first year, we went out to, this is Edinburgh, right, where you gave a talk basically detailing the work that we did with the adaptive optics system. And I don't know if I've told you this story, but I was in the audience. A couple of other senior AO scientists congratulated me on a great talk, and can't take credit for any of that. You'll hear a fantastic talk today. I give terrible talks. So, but they're also wondering when Maissa was going to graduate, and I was like, she just started. This is her first year, so big things are going to come. So they wanted to know when she was actually going to graduate, so they could hire her. So unfortunately, only one group managed to hire her as a postdoc. But anyway, so moving on. So in order to do the science that we needed to do, we needed an infrared camera for the adaptive optics system at Kitt Peak. So we got that in the next year. So this is a picture of a few of us at the IfA. Got this new SAPHIRA camera in to the IfA. We got it on the telescope very shortly thereafter. So here's Maissa with the infrared doer. We also have this up in the lab right now because we're getting it ready for another deployment. And of course, unfortunately, the telescope out there was kind of old, so it wasn't as efficient. And it wasn't until the end of our time out there that we actually roboticized the telescope. So in the meantime, we had to have telescope operators, and Maissa spent a lot of time taking all the data for her dissertation. So here's her in front of the controls at the 2.1 meter telescope. And you did a lot of this remotely as well. So this is just shows the sort of dedication that Maissa has to making the science happen. And of course, we also found that one of the filters we were using was a little leaky, so we had to go out again and replace it. So this is Maissa replacing a leaky filter. I think we put in the J-band filter here. And then, of course, this is Kitt Peak National Observatory. It's pretty accessible to the public. So they have a lot of sort of outreach events. And so there are a lot of people that came through, and Maissa volunteered to basically host some of the tours that were given up at Kitt Peak. So you can see her here basically talking to the public about our instrument and the science that we do, which is absolutely fantastic. Of course, all good things come to an end, so we had to pack it up at Kitt Peak. And this is Maissa making sure that all the cables were removed from the AO system. So she's in the yoke of the telescope here, one of the few people that could actually fit in there to get at the cables. So we're has many talents. Gave another talk, talking more about the science this time. So this was at Austin at SPIE conference. And now we're thinking about Mauna Kea. We started to plan out taking the system from Kitt Peak now to the 88-inch telescope at Mauna Kea. We were going to finish up the rest of the observations that Maissa needed for a dissertation. And some of the early work, we got the laser tested. Maybe this is 2017 or 2018. Maissa is basically putting some card in front of the high power laser, and then this is us looking at the return through the telescope. Everything was good, so we knew we could put the AO system up there. So we did surgery again on the adaptive optics system. So Maissa and I did that and got it on the telescope, which you can see here with the infrared camera. Happy grad student. And then again, taking lots of data. So this is a little stage. We don't necessarily need 4 people to take data, but Maissa was doing most of this solo, sometimes with backup help from Paul and James. And then, of course, what warms every advisor heart is once they have the data, starting to write papers. So, and of course, we had a celebration of the first Lasso paper earlier this year with a bunch of us out in the Lanai. And hopefully, and we have an accepted second paper now that we just found out about this past weekend. Just needs a few revisions and then almost ready for the third one. So with that, I'll hand it over to Maissa, who will tell us more about the wonderful technology and science she's been doing for the last 6 years.
Thank you. Right. All right, so move the Zoom controls. Okay. All right, hello everyone. Thanks for being here, and thank you, Christoph, for the great introduction. So today I'll be presenting my thesis called the Large Adaptive Optics Survey for Substellar Objects, or LASSO, at wide separations around young, nearby, low-mass stars. So my advisors are Christoph Beranek and Mike Liu, and my committee consists of Brendan Buller and Dan Huber and Jen Van Saters and Monique Shiba, who are also online. So my dissertation work had 2 main aspects. There's the adaptive optics instrumentation work, working on Robo-AO and the SAPHIRA camera, which then enabled the science consisting of large direct imaging surveys, searching for substellar companions. So here's a brief, slight delay. Okay. So here's the brief outline of this talk. So I'll go over some of the motivation behind this work. Then I'll talk about the Robo-AO instrument and the SAPHIRA detector. And then I'll go over the results from the Lasso Survey and the Robo-25 Survey. And then I'll finish with some concluding remarks. All right, so direct imaging is a complementary exoplanet detection method compared to other methods such as the transit or radial velocity methods, which have detected thousands of exoplanets. Direct imaging probes substellar companions that are more massive and at larger separations. And so the presence of these massive companions at wide separations generates a lot of questions as to how they could have formed so far away from their host star. So the main question is, how do we explain the presence of these massive substellar companions that are so far away from their host stars? In the same space, we find companions that are ranging from planetary to brown dwarf to stellar masses, and all overlapping in separation ranges. And so we're interested in understanding what processes lead to these different types of companions. How and why do they form the way they do? Are these objects, do they represent the high mass end of planets? Are they the low mass end of stars? Are they some type of new mechanism or mix of mechanisms? And another interesting aspect is how best do we classify these objects? The IU differentiates brown dwarfs from planets at 13 Jupiter masses, which is the deuterium burning limit, but perhaps there are better ways of differentiating these categories that are based on their formation histories. But the main challenge is that these are very rare objects. And so here's a summary of occurrence rate estimates from direct imaging surveys going back about 15 years. And so, for example, some surveys have focused on high mass stars, others on low mass stars, yet others on stars with debris disks, as well as some that are compilations of multiple past surveys. But the total number of stars observed in these different surveys are generally on the order of a few hundred stars. And so we need very large surveys to be able to detect enough of these companions to build up a sample to study them on a population level. So formation models predict different planet populations. So here you can see the distribution of companion masses and separations that are predicted from two different types of models. There's the gravitational instability, which is the more star-like formation scenario shown in red. And then there's the planet-like formation scenario, the core accretion, which is shown in blue. And so what we want to do is compare the distributions that these different models predict with the observed distributions that we see. But to be able to do this, we need to build up the statistics to be able to look at the observing frequencies of these different types of companions. So here's a recent census of directly imaged substellar companions, and you can see the range of companion masses and separations. And you can see the circles that are circled in black are the ones where we're starting to be able to measure orbital motion on these objects. And so that gives us a lot of extra information, such as the dynamical masses of these objects, and we can learn a lot about these systems and about how they might have formed or evolved. So now we're just at the point where we're just starting to build up enough statistics to start looking at the populations of these objects. So here you can see the eccentricity distribution of these substellar companions, and they're separated in the brown dwarf and giant planet categories. You can see that planets tend to form on more circular orbits, but they could have been excited to higher eccentricity orbits. But as you can see, we can just start seeing the peak of these distributions, but we can't really analyze these distributions in detail yet. Like we can't break them down into smaller bins or play around with the boundaries. And so we need more data to be able to really study them in detail. So M-dwarfs are by far the most common types of stars in the galaxy. And so there's a lot to learn from studying the diversity of systems around the most common types of stars. Another advantage of studying M-dwarfs when searching for substellar companions is that they offer more modest contrasts, and so we can more easily detect these substellar companions. And in addition, studying stellar multiplicity of young stars is also useful for placing boundary conditions on formation and evolution theories. So to give an idea of the motivation here, so what we want to do is to observe the diversity of substellar companions and their system architectures in order to analyze the population trends to place stronger constraints on models, with the overarching goal being of better understanding planetary and stellar formation and evolution. And the main challenge that these are rare objects, so what we need are very large surveys. So before jumping into talking about the surveys, I want to talk about the type of technology that we use to carry out the surveys. So adaptive optics technology corrects for the blurring effect of atmospheric turbulence on astronomical observations from ground-based telescopes. So you have light coming from a star that arrives as parallel rays, which is equivalent to a flat wavefront. And then as it travels through the Earth's atmosphere, it passes through pockets of air of varying temperatures and pressures, which then distorts the wavefront. So the telescope collects this distorted light. And the basic concept of AO is that we measure the distortion with a wavefront sensor, and then we correct the distortion by flattening the wavefront with a deformable mirror. So here you can see an image that you would get without adaptive optics. Then once you turn on the adaptive optics correction, you can actually see that this was 2 stars. So Robo-AO is a robotic adaptive optics laser instrument for 2-meter class telescopes. It uses a Rayleigh beam UV laser guide star system. And to correct for the tip-tilt motion of the star, we do post-facto shift and add. Robo-AO has the unique characteristic in that it's automated, so it operates very efficiently, so we can observe many, many stars. And it has less than 1 minute overheads. And so that's exactly what we need to carry out these large surveys. And here's a picture of the Robo-AO instrument, the optics inside, and on the right is a picture of the laser projector for the laser guide star system. So first part of my work was to help commission Robo-AO. So Christoph showed a bunch of cool pictures from that. And so the first part was realigning the optics in the lab before moving to a new telescope. And then after that, we commissioned on the Kitt Peak 2.1 meter telescope and then the UH-88 2.2 meter telescope. And I also worked on optimizing Robo-AO's performance. For example, optimizing the laser range gate system. So Robo-AO uses a Shack-Hartman wavefront sensor. And here's a basic illustration of that type of wavefront sensor. So we pass the light through an array of lenses. And these lenses focus the light on the detector as points on the detector. And so if there are no distortions in the light, you get this perfect grid of points. But if there are distortions in the light, then the points get shifted from this perfect grid. And so from these shifts, we can measure and sample the slopes of the wavefront. So now when we use a laser to create an artificial star for the wavefront sensing, we need to only use the laser return light that's from the layer where the laser's focused. Otherwise, we get a grid of points that looks like this, which makes it pretty hard to get accurate measurements. And so what we do is we use a shutter system to create nice spots like this. And so when we optimize the laser range gate system, what we do is we adjust the time delay for opening the shutter so that it corresponds with the laser focus height. And then we adjust the length of time the shutter remains open, which lets us sample a certain amount of the atmosphere layer. And so initially, Robo-AO worked in the visible. So we had a visible camera for the science imaging. And so part of my work was to commission a new infrared camera for Robo-AO so that we could simultaneously image in the visible and in the near infrared. So the type of camera is a SAPHIRA camera, which is a new type of infrared array technology, which is in development. And this effort was led by Don Hall here at the IfA, who unfortunately isn't with us anymore, but whose expertise was invaluable. So the SAPHIRA detector amplifies the signal through avalanche gain while keeping the read noise fixed, so you get very low read noise. And then it's sensitive from 0.8 to 2.5 microns, and this is the first long-term deployment of one of these cameras for science purposes. So here I show a bit of the structure of this camera. So the orange dewar is what surrounds the whole structure and seals it, which is vacuum pumped to isolate from the ambient air and to maintain very cold temperatures. There's a vibrating cryo cooler underneath. And then the radiation shield inside prevents the thermal radiation from reaching the detector. And the inner sanctum is where the detector is actually located, which is above the cold head that we cool down to 65 Kelvin and then heat back up to 85 Kelvin. And we used a cold blocking filter to select the band, the J, H, or other bands. All right, so to read out the detector, we read out with non-destructive reads. So that means that the signal increases with each frame until we reset the detector. And we read out at a speed of 20 hertz. The readout electronics were also developed here at the IfA by engineers Charles Lockhart and Eric Warmbier. And so here you can see a star with just the raw readouts. And so the blinking is from when we reset the detector. So we bin the frames to 0.1 seconds to correct for the tip tilt motion. So here you can see these binned frames and the star is centered. So now that we have an instrument that can observe very efficiently and carry out these very large surveys, and it's equipped with an infrared camera, which is what we need to observe these faint substellar companions. They're brightest in the infrared. So now I can introduce my thesis survey, which is Lasso, the Large Adaptive Optics Survey for substellar objects at wide separations around young, nearby, low-mass stars. So to build the target list for Lasso, we started with the Cool Dwarf catalog, which is part of the TESS input catalog. Then we cross-matched it with Galax to apply UV cuts to select for young stars. And then we cross-matched with Gaia to use the parallax measurements to select stars that are within 100 parsecs. Finally, we applied technical limit cuts based on the telescope's location and the sensitivity of the instrument. So we end up with a list of about 3,000 targets. And so the targets are shown here. You can see the range of temperatures about 3,000 to 4,000 Kelvin, and overlaid on top are isochrone lines. And so you can see that we expect most of our targets to be less than 300 million years old. We also have a list of stars from the SCOSEN association, which is the closest association at about 120, 140 parsecs. SCOSEN is divided into 3 subgroups. And the purpose of having the sample is to have a sample of stars where we have better age estimates and that are younger. And so then we can compare these stars with our Lasso stars. These stars are also more likely to have debris disks still, and so could be more likely to have companions as well. All right, so here I summarized the observations that were collected throughout my thesis. So first with Robo-AO, both at the Kitt Peak and the UH-88 telescope, I observed a total of 427 stars, which are the black X's on the plot here. And then I also observed a set of stars with IRCS instrument on Subaru and with NERC2 on Keck. Those stars were prioritized based on their likelihood of being young moving group members, so we would have better age estimates, and also stars that are accelerating, which would be more likely to have companions. And so those are all of the magenta stars. So in total, that was an additional 470 stars observed. So in total for the Lasso survey, I observed almost 900 stars. Most of them are Lasso stars and about 100 are SCOSEN stars. So to have an idea of the sensitivity of the Robo-AO instrument with the infrared camera, I generated these contrast curves by injecting fake companions at different contrasts and different separations, and then measuring how faint of a companion we could still recover. And so here are the contrast as a function of separation for the J and H band with Robo-AO. Now to give an idea of what this actually corresponds to in terms of companion, the actual companion itself, I converted these contrast curves by using the distance to the stars to get the separations in AU and the contrast to absolute magnitudes. Then I used isochrone models to compute the masses over a range of ages, so about 10 to 300 million years. And then I used the ExoDMC Python package to generate a sensitivity map for each target at each age. And so here we can see that about 50% of our observations were sensitive to substellar companions between 50 and 450 AU, and about 70% were sensitive between 115 and 230 AU. So to give an idea of how this fits into the larger context of other types of surveys, compared to extreme AO surveys, so for example, GPI, I show the contrast curves there. They're sensitivity maps, so they're more sensitive to closer in companions. And then on the other end, to the non-AO surveys, which are sensitive much wider companions. And so Lasso kind of fits in the middle between these two. So in total, with Robo-AO, we detected 121 companion candidates. So here are snapshot images of all of these detections. And then with the Subaru and Keck observations, we detected another 129 companion candidates. So now the next step is to determine which of these companion candidates are actually physically associated companions and not just background objects. So to do that, I compared the primary and companion candidate Gaia proper motion and parallaxes to see if they match. So here I show the difference in parallax over the primary star's parallax and the difference in proper motion over the primary star's proper motion. And if I compare it to a binary catalog of stars from Gaia, you can clearly see that there's two groups that emerge. And so once we place these thresholds, we can see that all of the gray triangles are the background objects, where there's a large difference between the primary and companion measurements. And then all of the green circles are the physically associated companions. So I also looked at how well Gaia could recover these companions. And so there's a RUI value, which is the renormalized unit weight error, which basically indicates if there's an issue with the astrometry, which uses a single star model. And so if there's a companion, then that model won't fit as well. And so a large RUI could indicate the presence of a companion. And so here you can see all of the X's are the companions that we've detected that we did not recover in Gaia. And all of the circles are companions that were detected in Gaia. So you can clearly see that companions that were generally within 1 arcsecond were not well recovered, but the star had a high RUI value compared to the systems where both the star and companion were well resolved. They tend to have lower RUI values. So here I show the contrast and separations of the 121 companion candidates detected with Robo-AO. The green circles are the physically associated companions, and the orange squares are the ones that still need to be confirmed because they were not found in Gaia. And then if I add all of the companion candidates detected with Subaru and Keck, now the total is 250. And again, we can see that mostly the unconfirmed companions are the ones that are very tight. And we expect most of these to be physically associated because they're so close. They have very low probabilities of being chance alignments. So here are, again, the companion candidates detected with Robo-AO and with SAPHIRA, the Subaru and Keck. And so I show the absolute magnitude as a function of the projected separation. And to give an idea of what those objects could be, if I overlay here these lines that show the threshold between the substellar and stellar boundary for different aged systems. So you can see that younger systems are the blue line at the top, and older systems, 200 million years, are lower. And in the Subaru and Keck data, you can see there's a handful of companion candidates that are very faint and could potentially be substellar, which we'll need to follow up on those. So we also detected 5 triple systems with Robo-AO. And so here I show those images. The A is the star and B and C are the companions. And you can see that most of them show this structure where either the primary star is on its own and the 2 companions are tight, or one of the companions is very close to the star and the tertiary companion is farther out. And so this hierarchical structure is what's reached as orbits stabilize. And here are more triple system candidates from the Subaru and Keck observations. And again, we can see this hierarchical structure in most of these images. So as I mentioned earlier, with Robo-AO, we can observe in the visible and in the infrared simultaneously. So that means that we can get optical infrared colors. So I-J or I-H colors. So on the left here, I show the absolute J magnitude as a function of I-J, and on the right is the same for the H band. And so you can see the companions that have arrows, those are the ones where we did not detect them in the visible image, so we can only place limits on their colors. And to give an idea of what those companions correspond to, so here I show the orange line is the Krauss and Hillebrand SED, and most of the companions that land on this line are likely stellar companions. And the shaded regions show the substellar stellar boundary for different aged systems. So I want to point out a couple interesting objects in here, which are these two, which are very faint and red. And so these are, one of them is a brown dwarf, a 43 Jupiter mass object that was previously reported in the literature. And the other one is an object at the stellar and substellar boundary at 81 Jupiter masses, also previously reported in the literature. And here, all of the black dots are the ones that we've followed up with Keck to get J, H, and K photometry. So here, I show those results from the Keck images. So I show the absolute magnitude in J as a function of J minus K, and then the J minus H and H minus K colors. And the lines here show the different spectral types for corresponding to these different colors and magnitudes. So you can see most of the points that land again on the orange line are likely stellar companions. And then there's a few more that we'll need to follow up to determine exactly what their nature is. So I also searched for our companions and our observed stars in the Hipparcos Gaia catalog of accelerations. Stars with measured accelerations are particularly interesting because we can measure dynamical masses and get orbital information from those accelerations. And those accelerations are changes in the proper motion from the Hipparcos and Gaia measurements with about a 24-year time baseline. So here, the dark blue cumulative distribution are for the stars where we did not detect any companions, and it's as a function of the acceleration significance. And the light blue line is for the stars where we did detect companions. So you can see that the majority of the stars where we did detect companions, they have high significance of acceleration, while the majority of the ones without companions detected don't have significant accelerations. And now if we look at the significance of the acceleration for the systems with detected companions as a function of the separation to the companion, you can see a clear trend where tight companions have higher significance of accelerations on the primary star, while the farther out ones do not. And the circles, again, are the physically associated objects, and the squares are the ones that are to be confirmed. But the square that's shown here, where the star has a high significance of acceleration, is very likely a true physically associated companion. So to summarize the yields from the Lasso survey with Robo-AO, so for the cool dwarfs, about 24% of our observed stars had companions. And if we compare this to literature values for the occurrence rate of companions around cold dwarfs, which is about 27%, those two results are consistent within error bars. For the higher order systems, we get a occurrence rate of about 1.2%, and our field of view is about 35 arc seconds, and compared to literature values, about 5%, but those are for much wider separation ranges. That's likely why our values are lower, because we're probably missing many of the wider companions. And for the substellar companions, we get a range of about 0.5 to 1.5%, depending on some of the follow-ups that we'll be doing, and compared to the 1 to 4% occurrence rate estimate. So our values are likely lower because we don't have the sensitivity in all of our observations, as I showed in the sensitivity maps earlier. So now we're switching gears to another large survey that was part of my thesis, the Robo-25 survey. So the goal of the Robo-25 survey is to evaluate stellar multiplicity rates for all types of stars in the solar neighborhood. So although studying young stars has many advantages and is particularly informative about formation and evolution mechanisms, star-forming regions tend to be farther out, where it's harder to study fainter stars, and so it's harder to have complete samples. So studying nearby stars is advantageous in that regard because we can detect even the faintest stars and they can be counted. And so we can also probe for companions at tighter separations. Stellar multiplicity properties vary strongly with stellar mass. So there's a lot to learn from comparing companion populations around different types of stars. So here, what we want to do is create a AO census of tight companions to stars in the solar neighborhood, so that we can then analyze in detail stellar multiplicity rates and companion population trends. So our original target list for the Robo-25 survey was built by the Research Consortium on Nearby Stars, or RECONS, which is led by Todd Henry. And they measured the distances to stars with ground-based parallaxes. Then we updated that list with Gaia EDR3 parallaxes. So in total, I analyzed 1,157 stars of all spectral types within 25 parsecs. And here you can see the distribution of spectral types for the stars in our sample. And not surprisingly, the M dwarfs are the biggest category. These stars were all observed with Robo-AO in the I band at the Palomar 1.5 meter telescope. So we want a uniform distribution of stars that are sampled throughout a volume and without being biased to brighter stars. So to evaluate the completeness of our volume limited sample, we use the VV max statistic, which is basically a ratio of the volume enclosed by each star over the maximum volume of the sample. So you want the average of these ratios to be 0.5 to correspond to 100% complete sample. So here you can see our completeness for different distances in our sample. So at about 15 parsecs, we're 90% complete, and out to the full 25 parsecs of the survey, we're about 78% complete. And then if I break this down into the different types of stars in our sample, so you can see that the F, G, K, so the green, yellow, and orange samples are pretty complete. And then the A and white dwarfs are much smaller samples, so we can't expect those to be complete. And then the M dwarfs, I split the early M and late M types because most of our sample is early M types. And they have about a 66% completeness at the full 25 parsecs. So with this survey, we detected 154 companion candidates within 4 arc seconds with Robo-AO. So again, here are snapshot images of all of these detections. And here are the contrasts and separations of these detections, where again, the green circles are the physically associated objects and the orange squares are the ones that still need to be confirmed. We also detected several triple systems. So here I show 4 triple systems where both components were within 4 arc seconds. And here I also show an even higher order system where we imaged 4 stars, 4 M dwarfs, and it's actually a quintuple system where one of the stars is a spectroscopic binary. And so keeping in mind our goal of evaluating the multiplicity rates of the stars in the solar neighborhood, to complement the tight Robo-AO search for companions, we also searched for wider co-moving companions with Gaia EDR3. And so with that, we detected an additional 147 companions from this wide Gaia co-moving search. So in total with the Robo-25 survey, we have 301 companion candidates in our sample. So again, I compared the parallax and proper motions of these companions with their primary star to determine physical association. And I searched for our systems in the million binary catalog from Gaia EDR3, which came out earlier this year. In this catalog, they calculate this R value, which is a proxy for probability of chance alignment. So very low R value means a very low probability of chance alignment, and so very high likelihood of it being a physically associated object. And here I show the cumulative distributions of the RUI values, so the renormalized unit weight errors from Gaia. And so the red sample are the ones where we don't detect companions, and so you can see the majority of those have low RUI values. And the green sample are the ones where we detect companions within 1 arc second, and the vast majority of this sample have high RUI values. And so again, here I show the recovery from Gaia of our companion detections from the ones detected with Robo-AO within 4 arc seconds. And so the X's are the ones that were not detected in Gaia. And again, we see the same trend where the ones that are not detected in Gaia, the primary stars have high RUI values compared to the systems that are well resolved, where the primary star has a lower RUI value. And the dotted line, horizontal gray lines, connect companions that are orbiting around the same primary star. So those are triple systems. So you can see there's a couple companions that are at wide separations, but the primary star has a high RUI value, and that's likely because of the presence of the inner, tighter companion. So I searched for our stars and our companions in the Gaia, Hipparcos Gaia catalog of accelerations. And so here you can see that the dark blue line are the ones that are where we did not detect companions, and then the majority of those have low significance of accelerations. While the green line at the bottom, 91% of the systems where we detect a close companion have a high significance of acceleration. And here you can see the significance of acceleration as a function of the projected separation of these companions, where the orange squares are the ones that still need to be confirmed, and those tend to be the closer in companions. And the green circles are the ones detected with Robo-AO that are physically associated, and the purple stars are the ones from the wide Gaia co-moving search. And again, the dotted horizontal lines connect systems that are triple systems orbiting around the same star. And it's likely that many of the stars where we don't detect companions but have high significance of accelerations, it's possible that many of those have unresolved companions. All right, so we've probed separation ranges from a few AU out to 10,000 AU with the Robo-25 survey. And so here I show the multiplicity rates for the different spectral types of stars in our observations. So we can see that the expected trend of higher mass stars having higher multiplicity fractions is seen here. But now what we want to do to estimate the multiplicity rates is to correct for the unresolved companions. And so to do that, we took our sample of stars that have either high Rui values but no detected companions, or that have high significance of accelerations but no detected companions. And if we use those to estimate how many of our stars have unresolved companions, then we recalculate our multiplicity fractions. And so these are the new shaded bars in this graph are the corrected multiplicity fractions for the different types of stars in our sample. And so now if we compare our values with literature values, so for FGK stars, we get about a 41% multiplicity rate, which compares to 44% in the literature. For M dwarfs, we get 28%, which compares with the 27% in the literature. And so we can see that our results are consistent. All right, so to summarize, I worked on the instrumentation aspect of my project on the Robo-AO instrument, which involved realigning some of the optics in the lab, commissioning the instrument on 2 different telescopes, and then optimizing its performance and installing a new SAPHIRA detector. I carried out the Lasso Survey, where we observed and analyzed almost 900 stars with AO images of young nearby low mass stars, and detected a total of 250 companion candidates, the majority of which are stellar, and a handful of them which we're following up to determine if they could be substellar. I determined physical association status with Gaia, and also found that a higher proportion of stars with detected companions have significant accelerations, and that this correlates with the separation of the companions. And for the Robo-25 survey, I analyzed 1,157 stars of all spectral types within 25 parsecs observed with Robo-AO, and combined the Robo-AO tight detections with the wide Gaia co-moving search, and detected a total of 301 companion candidates, and evaluated the Gaia companion recovery, and also reported multiplicity fractions by spectral type. So I've been very fortunate to be able to work on a multidisciplinary project. I directly worked on an instrument, then used it to collect the data for my survey and then analyze it. And I plan to continue working on both the instrumentation and the science aspects during the next phase of my career as a postdoc at the Santa Cruz Extreme AO Lab. And I'm looking forward to seeing and hopefully contributing to advancements in both technology and in our understanding of substellar companions. Looking ahead, I see advancements in AO and detector technology combined with the next generation of large telescopes and space missions like the JWST that's about to launch. This will increase our sensitivity to detect even fainter planets, probing a wider range of companion masses and separations, so expanding our population of directly imaged substellar companions. And with the upcoming very precise astrometry measurements, like from the full Gaia DR3 data release, this will allow us to detect these companions much more efficiently by targeting stars that show signs of likely harboring companions. So not only will we be able to probe a wider population of directly imaged substellar companions due to more sensitive technology, but we'll also be able to conduct targeted searches for these companions, which will allow us to grow our population at a faster rate. So I'm really excited to see the new discoveries that lie in our future so that we can carry out these detailed population level studies of these substellar companions and unlock some of the mysteries of these rare systems. And hopefully I'll be able to contribute my piece to this puzzle. So now I'd like to take some time to thank everyone who has helped along the way. So first and foremost, I want to thank my advisors, Christoph and Mike. Thank you both for your guidance and your feedback throughout all this on papers and proposals. I've learned a lot of skills from both of you that I'll use throughout my career, and I've really appreciated it, so thank you. I also want to thank my committee, Brendan, Dan, Jen, and Monique for your guidance and feedback through multiple committee meetings and other discussions. So thank you all. I also want to thank the Robo-AO team and everyone who has helped at both Kitt Peak and UH88, from making this really cool instrument work to the many long nights at telescopes. I also want to thank everyone who has helped with the SAPHIRA camera work, from the lab work to understanding unexpected noise sources and answering my questions. I also want to thank the Kitt Peak and Mauna Kea Observatory personnel for making the many, many nights of observing possible and getting all these really cool images. I also want to thank the IfA Hilo faculty for many interesting discussions on both the science and the instrumentation. And I want to thank my classmates, Christian and Karina, honorary classmate, Travis and ZJ, Ben, Denise, Xiao, and Jia, for going through these years together and helping each other out and being a very supportive group. I also want to thank the Hilo grads and postdocs, Ryan, Max, Charlotte, and Charles-Antoine, especially for keeping me sane through the last stages of my thesis. And I want to thank the rest of the IfA grad students and postdocs and faculty and staff for making this place what it is. I want to thank also Sandra and Suzanne, who helped me with many travel arrangements and getting all the paperwork done, and Bill and Amy and Pam and Kurt and Rashang and Melissa for helping with setting up today, for example, and just helping in general when I needed anything. I want to thank Jess and Kelly and Larissa for always being very supportive and giving me the confidence boost when I needed one. And I want to thank my friends from back home who have kept me sane through all the years, and two of them are here today, Leanna and Ali. Thanks for coming. And I want to thank my family, who's always supported and encouraged me. Some of them are watching this at 1 a.m. in France right now. And finally, the biggest thanks to my parents, Farid, Josie, and my sister Amira, for always being so supportive and who are here today as well. And yeah, I wouldn't be here and where I am today without you. So I dedicate this to you. All right. Thank you. Any questions?
Excellent talk, Maissa.
Thank you.
All right, so now we'll take questions from the audience here, and if there's anybody online, you can send questions there too, and I'll read them out. I'll do this for about, well, as long as we have questions, maybe 10, 15 minutes, and then we'll close it for the committee to talk with Maissa. So any questions here? Nobody. Anybody in the back? All right, you're getting a lot of comments online, which are good. Michael.
Can you talk a little bit about the Robo-25 survey and how it compares to previous surveys like recons or anything like that?
Yeah. So the Robo-25 survey, the main purpose for us was to detect these tight companions with Robo-AO. Many of the other surveys didn't necessarily use AO, so they weren't sensitive to these tight companions. I think that, yeah, that was the main point, and the fact that with Robo-AO we can observe over 1,000 stars pretty quickly. The data was collected within a year, basically.
Mm-hmm.
So yeah, that was one of the main advantages, just observing a bunch of stars.
Any other questions? Go on Zoom, huh? Just compliments online so far.
Thank you.
Not really a question. Okay, well then, if we don't have any, then we might as well call it a day.
Fine with me.
So let's give Maissa another round of applause.